All right, and welcome to Unit 4, Conservation of Energy, Lesson number 1 on work. And in this video, we are going to be going over example number 2. All right, so this example starts off with a 17 kilogram block, and it is being pulled to the right by force number 1. Well, it doesn't tell us what force number 1 is, but this block is also being slowed down by a force of friction, which it has been kind enough to tell us has a magnitude of 120 newtons. So where do we go from there? A little bit more information is given. This block is decelerating, has an acceleration of 1.85 meters per second to the left, and it is decelerating because of friction. And the initial velocity of this block is 9 meters per second. So over some amount of time, this block is going to start at 9 meters per second, slow down, and eventually stop to rest, or 0 meters per second. This question is asking us to determine the work done by this force 1. So we'll say we're looking for this in order to bring it to rest. Okay, well, I think that's within our capacity here. Let's switch our colors up and start solving. I'm just going to start with this work formula here, and I'm going to say work is equal to force times distance times the cosine of theta. All right. Right off the bat here, I'm going to get rid of this cos theta because what do we have? We've got our initial velocity is to the right, and our force 1 is also being applied to the right. It's in the same direction. So this is cosine of 0 degrees. Cosine of 0 degrees is equal to 1. So I'm just going to cross that out because anything multiplied by 1 is just itself. So we're just going to start off with work is equal to force times distance. Okay. Well, issue. We're solving for force first, so we don't have this yet. Also, we don't have distance yet. But when we do, we can figure out the work done by force 1. So that's good. We know that we can do it, we just need to get these values first. How are we going to do about that? Well, let's do a little bit of kinematics, or not kinematics. Well, we will do some kinematics, but we're going to start with dynamics. Start with magenta here. And we know that force net is equal to mass times acceleration. And we also know that force net is equal to the sum of all of our forces. So force of friction plus force 1. All right. And we have a couple values we can fill in here. We know mass, we know acceleration, so we can figure F net out right away. F net is equal to 17 kilos times negative 1.85 meters per second squared. Right, I'm choosing negative 1.85 meters per second because it's decelerating us. So our F net works out to, well, actually, I'm not going to solve that yet. I'm just going to take these values and plug it into this formula because honestly, on my sheet, I didn't solve it. And we also know force of friction is going to be negative 120 meters. So for this formula here, let's put 17 kilos times negative 1.85 meters per second squared is equal to force of friction, so negative 120 newtons plus force 1. Do some rearranging. This is going to be some negative number plus some number 120. And we're going to get a force 1 value of 88.5 newtons. Okay. So let's underline that value. Useful for us for sure. F1 checked off. Now we need to find displacement. Well, we could do some kinematics here. Let's drop into blue. And we can say that we know VI. VI is equal to, well, you know what? Let's just write them all. We have them all written out here. We have acceleration. We have initial velocity. We have final velocity. That's three things right there. We have three things. We want to find displacement. Well, there happens to be a formula for that. We can use this thing. Final velocity is equal to VI squared plus 2 times acceleration times displacement. And we can rearrange that formula. VF is 0, so it's going to cancel out. And we'll have distance, or displacement, I guess, is equal to negative VI squared over 2 times acceleration. Put some numbers in here. You can say that negative 9 squared. And now remember, this is going to be like 0 minus 9 squared. So this negative's on the outside. So this will still end up being a negative 81 value over 2 times our acceleration. What was it? Negative 1.85 meters per second squared. And we end up getting a displacement value here of 21.89 meters. Okay, another useful value. We can check that one off. If we're looking for the work done by force 1 now, we now know the magnitude of force 1. We know the distance at which force 1 acts over. We know it's acting in the same direction as the motion. So let's plug numbers in and finish this off. Work is equal to force 1, which was 88.5 newtons, times our displacement of 21.89 meters. And we get a work value here of, I'm going to put it straight into scientific notation, 1.94 times 10 to the 3 joules. And that's it. That's the final answer for example 2.